Hello friends, welcome to our channel. Let's have a look at problem 3533, Concatenated Divisibility. This problem is marked as hard. However, if you have practiced a lot on backtracking, this problem might be not that challenging, right? In this video, the method we are going to use is the recursive backtracking. Also, we are going to use bitmask. So here, I'm not going to read through the problem statement because the problem statement is short and you can read through. But there are several points I want you to notice. The first is that, so if we do concatenation, then how to compute the result of concatenation. For example, if you have two numbers, 12 and 45, then if you concatenate, so you get 1,245. So the way to compute is that actually because the length of 45 is 2, 12 is shifted to the right by 2 positions. But this position is 10, base 10. So we should multiply this 12 by this 10 to the power 2. And then add the second number, 45. So we get 1,245. So similarly, if you concatenate 33 and 1245, so you should multiply 33 by 10 to the power 4 and then plus the second number, right? So this is the one thing. The second thing we want to notice that is the lexicographic smallest permutation in the sense of a list of integers. So here if you compare, I just want to give two examples. So 3 and 12 and 12 and 3, because 3 is less than 12. Therefore, the first list is less than the second list. So if you look at the second example, the first two elements are the same, but the third one we have 8. Also the second one has 12. 8 is less than 12. Therefore, the first list is less than the second list in the sense of this problem, or in the sense of a list of integers. So here also the third one is a rough estimate. So here the length of the nums can be up to 13. But if you compute the upper bound of permutations with 13 elements, maybe 13 distinct elements, right? So we need to make this assumption when we do the estimate. So this will be factorial, 13 factorial. So this is the computation result. This is a large number, right? Therefore, we need to think of time complexity or consider cache, right? So with that said, we are ready to do the coding. So actually the coding will be self-explaining. So let's first do one version using decorator, and then we are going to write a version using specific dictionary as cache. So here using a decorator. So first, because of this assumption, the return, we need to do a sort for this nums. This is crucial. So I'm going to do nums sort. And another thing I want to do is to get the length, right? So we put it here just for convenience. And then we are going to write a recursive function to do the backtracking, to try to concatenate to get the result. So here I'm going to initialize a temp. So this is going to hold the valid divisible concatenation. And then I'm going to write a function. So I'm going to use mask, right? So mask and the current value. So the mask will tells us which number, which element in the nums has already been used. For example, let's say, let's use this as point 4, mask. So for example, in this example, the length is 3. If all the numbers are used, so we are going to see this bit position 0, so you get 1. Bit position 1, you get 1. And bit position, you get 2. So this corresponding to 7, right, in decimal. In other words, if your mask is 7, it means that all the elements are used. So in short, if bit position is set, in other words, is 1, right? Is 1. Or you can see a bit position, let's say I is set. So this is equivalent to say the mask and so 1 up to this position. So you are going to get 1, right? If a bit position is set, it means nums I is used, right? So this will be the rationale. So now with that, with those noticed, let's write the function. First, if mask equals this, say 1 shift to the right in units, n is the length, right? Minus 1. This corresponds to this one. For example, here n is 3, so it corresponds to 7, right? 2 to the power 3 minus 1. So this is the one. Every elements are used, and the current as a remainder should be 0. If this is the case, so we're going to return the state of temp. So this is the one thing. And then we are going to do a scan for this list to see which numbers are not used. If not used, we are going to try that, right? So basically for j in range n, right? So then we want to check if the element nums j is already used, right? If used, we just need to ignore that. If j nums j is used, we just continue, right? How do we check that? If mask and 1 shift to the right, left. So here the shift to the left, right? Shift to the left j unit. That's here. Here is I, right? So if this is the 1, right? Let me write with so this is not 1. This will be 2 to the power j. Let's just write it. If it's not, it's going to give you 0, right? So if this is not 0, then we're going to continue, right? So now if nums j is not used, what should we do? So now let's use this element. So it's a new mask. It's going to be add this bit, set this bit position. That will be 1 shift to the left j units. So the temp. So I'm going to append this nums j because we are using this one. And in order to make the new current, so we use this item 1 to compute the concatenation result. So it will be, the new current will be current times 10 to the power the length of nums j. So in order to compute the length, we first translate it into a string. So and then we just call the length method. So here we should modulo this key. This is due to this problem requirement. And then actually we can modulo this key again, right? So here, this is the first point here. So with that said, so we have the new mask and we have a new current. The new mask actually seeing that I also use the j in my temp and see if I can get a valid permutation. So now the answer will be recursive call it self call. So new mask and new current, right? So if answer, in other words, if there's something returned, it means that this gives us a valid one. So we are going to return answer, right? Otherwise, so what we do? So we do backtracking, right? Temp pop this one. So we are not going to use nums j as the present step. So we try others. So this would be the major part. So I guess with this one, we can basically call this function. So we start from 0. So the mask should be actually from 0 to 2 to the power n minus 1, right? So originally you have 0. So what we want to do is return result if result. Otherwise, so we're going to return empty. So as we estimate, actually, if you do like this, actually there's a lot of computations, a lot of try and errors, then it might not pass. So, but let me first check. Can't access local variable new mask. So here new mask equals mask. This will be good. Now let me see where I make it wrong. So we have this one, we have sort, a temp. So this will be 1 2 to the power n minus 1, and this 0 return temp for j in range n. So if mask and this is right, new mask and temp append nums j is also right. And let's see. So here, let me write like this: length of string nums j. So here I'm going to write like this: t. Oh, so here actually I forgot something. I forgot to add the second number, nums j, right? Now this will be good. Yeah. So this passes the 3 test cases, but if you submit now, it will get time limited problem. Let's demonstrate this to you. It will take some time to give us the time limit. Yeah, time limit exceeded. So now the thing is to do a decorator. So we use func tools, basically cache, right? So now let's run it again. Yeah, it will pass all the test cases. So here I'm using decorator. If you are not very familiar with decorator, let me provide you another format. So here I'm going to copy this part and make some modifications. So here I'm going to change this one to be version v1. So now I'm going to use a dictionary, right? So without this, we are not going to use this. But before we do that, so what we do? So we get a cache, right, as a dictionary. And then we do this function. What we do? So if mask and current in cache, so we're going to return cache mask and current. So you can write it like this. So this will be passed as a list, as a tuple, but writing as specifically as a tuple, it's more readable. So we have this, and then we continue, and so once you arrive at here, right, after you do the pop, so you can do cache and mask and the current equals answer, right? So this way will play the same role as the cache here in the first version. Now let me first run it to test the functionality. Yeah, it passes the 3 test cases. So now let's look at the generic case. Yeah, it passes all the cases. So I would suggest that if you are familiar with the function decorator, especially cache, and also another one is, let's say this one, least recently used cache. So you can pass a maximum size to be none. So this is also good. Let me check this version also. This is the version v2, right? So let me check. Yeah, it still passes. So here there are two possibilities. You can use function func tools cache. That would be good. Or you can use this one. Least recently used cache with maximum size none. Basically, do not restrict size. So otherwise, if you want to even from scratch, so you can use this format. So this is the first comment. The second comment might be that actually, though the problem is marked as hard, so once you notice these 4 points, one is how to compute the result, and lexically graphics small, and the runtime estimate, and also the mask, then this will be a standard backtracking problem. Then you can write this code as backtracking. So with that said, I guess that's it for the current problem and the current video. Thank you for watching.